Good morning, students. Today we will learn about one new topic from your fourth unit of Introductory Quantum Mechanics, which is variational method. Variational method. So, what is variational method? Okay, by variational method of approximation, it is one approximation method. Okay, na? We estimate ground state energy. We estimate what? Ground state energy for system for which we know Hamiltonian, but we don't know any wave function. Okay, so by variational method, what we will do? We will do it is an approximation method. So by this method, we estimate estimate ground state energy for system. Okay, now we estimate ground state energy for the system, and for this system, we know the what we know the Hamiltonian, means we know the eigenvalues. Okay, Hamiltonian is nothing but energy, no, and energy is what? Eigenvalues. So for which we know Hamiltonian. Okay, we know Hamiltonian, but don't know or we don't have any knowledge. We don't have any knowledge of wave function. Okay, na? It means that H means Hamiltonian, it is we know, so it is known, and psi, the wave function, unknown. Okay, and what we estimate here? Ground state energy. Ground state energy. Okay, now, so it is approximate, we will calculate. Okay, now, so by variational method, what we will calculate? Ground state energy we will calculate, and for which what is that? Hamiltonian means energy. Any atom, so many energy states are there, no? So that energy state we know, but we don't know the wave function. Okay, so by variational method we estimate or we calculate the ground state energy of the system. Okay, so sometimes we can find some excited state also. It is not only for ground state. We can also find first excited state, second excited state also. But mainly we use that variational method for ground state, for estimate the ground state energy. Okay, students. Now what is the question? The question arise here that when you can estimate first excited state or second excited state. Okay, now. So mainly we use that variational method for ground state energy, but we also find out first and second excited state energies. No, so when we estimate these energies also, so the answer is when Vx means potential is even potential. When potential is even potential. Okay, or symmetric about y or symmetric about y-axis. So symmetric about y-axis means what? Uh, the best example is harmonic oscillator. You know that this type of diagram in your book. Okay, this is axis, this is y-axis, and one potential which is symmetric about y-axis means it is like this side and this side, symmetric. So it is simple harmonic oscillator diagram. Okay, students. So at this time, when the potential is symmetric about y-axis, at that time we can estimate or we can calculate the first and second excited state also. Okay, by variational method. Okay, students. Now, variation method of approximation is based on what? It is, or this method. This method is based on. This method is based on variational principle. Variational principle. Okay. Now, what is variational principle? So, variational principle gives what? An upper bound state ground state energy. Variational principle gives us an upper bound ground state. What is the mean? I will tell you. First, we will write. So, upper bound ground state energy. And according to it, please write all these definition in your running notes, students, because these are very important. So, in easy language, I am telling you. Okay, students?
Okay, ma'am.
Are you getting me?
Are you getting
Okay,
me?
ma'am. Yes, ma'am.
Yes.
Okay, okay. So, according to it, ground state energy is less than or equal to expectation value of Hamiltonian in any normalized arbitrary state. Okay, now we will see what is that principle. Variational principle gives us an upper bound ground state energy. Upper bound ground state means can't be more than. It can't be more than. Okay, so can't be more than means any Hamiltonian or any excited first excited or second excited state or any energy state from any energy state, it will always less than. It will always less than. It means upper bound state. Okay, so that ground state means EGS is always less than or equal to Hamiltonian. Okay, Hamiltonian. So here we can write this also, psi average approximation. No, that's why get psi h psi. It is just one small formula which you have to remember. Okay, where psi is what? Psi is that normalized any arbitrary ground state function. Okay, students, so this is your variational principle. Now we will see the proof according to your notes. Okay, what is the proof? We will take here normalized wave function in the form of phi and ground state energy is E naught. Okay, so I am writing here, it is integration of phi star h phi d tau is always greater than equal to E naught, or E naught is always less than equal to this. Okay, this term. E naught is ground state, and variational principles show that this energy state, this ground state energy state, is always less than or equal to the other energy states, or Hamiltonian. Okay, so now we will prove that how we will prove. See here, Schrodinger wave equation is h psi is equal to E psi, no? So h psi is equal to E naught psi we are taking here. Okay. So it is uh, lowest energy. This E naught is lowest energy or ground state energy. So how can we write? First we will solve this phi star. It is h minus E naught phi d tau. We have to solve this, and this will be um, e greater than equal to this E naught. Okay. So how we will solve it? This is equal to, first we open that bracket, integration of phi star h phi d tau minus integration of phi star E naught phi d tau. Okay. Now we know that this is operator and this is normal energy state. So operator, there is not any change in that uh, integration. So it is integration of phi star h phi d tau minus, this is integration of psi star psi d tau is equal to what? 1. So integration of phi star phi d tau is equal to 1. So what is here? E naught. This is equation 1. Okay, students, are you getting me?
Yes, ma'am.
Okay. So now what we will do, the complete orthonormal set of that Hamiltonian is the complete orthonormal set, or we can say that the solution of this equation. The solution of equation is phi is equal to summation of n a n psi n. This is the solution of this equation. Okay. Now what we will do, we put the value of phi in this equation. So how is equal to, in this equation, in equation 1, we are putting at the place of phi, we are putting summation of a n psi n, and at the place of phi star we will put a n star psi n star. Okay, students. So integration of phi star e, in which equation they are putting, in this equation, in that side, in equation 1, that side. Okay. So h minus E naught, at the place of phi they are putting summation of n a n psi n d tau. This is equation 3. Okay. Now again they are taking this equation and solve. How they are solving? They are putting that phi and phi star value. How? Integration of phi star h minus E naught phi d tau is equal to, first put the value of phi star, which is this summation of n a n star psi n star into h minus E naught. Phi value is summation of n a n psi n d tau as it is. Okay. Now summation of n common, summation of n put outside, not common, because we cannot put two summations here. Okay. So summation of n, then integration of a n star a n also we can put out. Okay. this into what is here? Here is psi n star, that h minus E naught psi n d tau. Now you can see integration of psi star psi d tau is equal to 1. So summation of n is here a n star a n, this all 1. So here h minus E naught. This is equation 4. Okay. Now we know that these this term, these all terms are positive. No, this is positive. So this all term is positive. So what we can say that this h is greater than equal to h naught. Sorry, E naught. So the h is greater than equal to E naught because this whole term is positive. Okay. So how can we write this once again? See here, integration of, first write that term, phi star h, phi star h phi, phi star h phi d tau minus integration of phi star E naught phi d tau. So this is 1, no? Already we see in that this equation 1, integration of phi star h cap phi d tau minus E naught. So minus E naught is equal to this summation of n a n star a n h minus E naught. Okay. Now, so integration of phi star h phi d tau is equal to this E this side. So it is we can write this because this is positive value. So this minus E naught is always greater than equal to 0. Okay. So integration of phi star h phi d tau, put this E naught this side, so it is greater than equal to E. True. Okay, students, just to see this video again and again and you can practice for this principle. Okay, na? It is very easy, but you have to do practice. Okay. If there is any doubt, so ask me, student. No doubt. Shall we go?
No doubts, ma'am. Oh, yes, ma'am.
Now, application of variational method. Application of variational method. So application of variational method, what we already actually solved this equation. We already solved in our last chapter. Sorry, in our yesterday or day before yesterday topic. What is that? It is physical significance of some. I told you, no, that physical significance of non-degenerate perturbation theory. Okay, now. So that is that topic. That topic is again they are explaining a little bit in the form of applications of variational method. Okay. So we use variational method where with simple function to obtain an upper limit to the ground state energy of helium atom. Helium atom we already took in that. Okay. So some one nucleus is there and two electrons revolving around it. This distance is r1. This distance is r2, and the distance between these two electrons is r12. Okay. So one Hamiltonian we found there, what is that? Minus h cross square by 2m del 1 square minus h cross square by 2m del 2 square minus z square by r1 minus z square by r2 plus e square by r12. Have you seen this equation?
Yes,
Have
ma'am.
you seen this equation in our last topic?
Yes.
Okay,
Yes,
na?
ma'am.
Yes, that is energy which we can find with this variational method also. Okay, so we common this h cross square by 2m common inside del 1 square plus del 2 square minus z square common here 1 by r1 plus 1 by r2 1 by r2 plus e square by r12. Okay, so this is equation where what del 1 and del 2 are what? It is Laplacian operators. Okay, these are operators for first and second electron. Okay, this and this electron. Okay, na? And R1, R2, we know that what are R1 and R2? The distance between electron and nucleus. Okay, distance between first electron with the nucleus is R1, and distance between second electron with the nucleus is R2, and the distance between these two electrons is R12. Okay, na? So now wave function. It is also okay, this psi R12, R1 comma R2 is equal to psi R1 psi R2. Okay. Now psi R1 and psi R2 value already This is already you uh, already saw in your last topic. It is z cube by pi a naught cube into e power minus zr1 by a naught into psi 2 also z cube by pi a cube into e power minus z r2 by a naught. Okay, so it is like this. uh, I am doing some mistakes, I think so. Oh yes, root is there, I forgot to write root. Okay, root under root of z cube by pi a naught cube into this e power z r1 by a naught, then root. So when we multiply these two, so root will go no. So here z cube by pi a naught cube into e power, these both are same no, so we can write minus z by a naught into r1 plus r2. We can write like this also. Okay, now here z is equal to how many? 2. 2 electron, no? 2 particles. So this is now a naught is equal to what? A naught is equal to h cross square by M.Sc square. This is also in your first topic, which is non-degenerate perturbation theory. Okay. So now what we will do, that R1 is equal to, sorry, R is equal to, now total energy we have to calculate, which is potential kinetic energy plus potential energy. Okay. So first that R is equal to z square e square by 2 a naught. V is equal to minus 2 z square by a naught, because 2 electrons now, so we are taking 2 here for potential energy. Now, oh no, for potential energy, for 2 electrons we have to multiply by 2 right now. Okay, it is R is equal to 2 into Z square E square by 2A naught, and potential energy what? 2 into 2, 4. So 4 Z square by A naught. A naught is this, sorry. Okay. So it is now uh, what we will do now? Now total Hamiltonian, which is what? Ke plus Pe. Kinetic energy plus potential energy. Okay. So which is this 2 to cancel here. So Z square E square by A naught plus. So here minus, so minus 4 Z square by A naught. Okay. So this is your potential energy for unperturbed term. This is your potential energy for sorry. This is your Hamiltonian for unperturbed term. Okay, means for ground state. Now for first excited state or any perturbed term, we have to write one more term is here, which is E square by R 1 2. Okay, you know in this equation the first term means these two terms are unperturbed term, shows unperturbed. Unperturbed means non-disturbed. Okay, these terms are non-disturbed. And this is perturbed term, means excited energy state, perturbed term. Okay, so in total Hamiltonian, we have to calculate this also. Okay, student. Now we calculate this term and put in this equation. Okay, now we will calculate and put in this equation. This is your last derivation. First, just 5 minutes it will take. Okay, so E square by R12 is equal to double integration of psi star of R1 comma R2 into E square by R12 psi R1 comma R2 d tau 1 comma d tau 2. This is also you already calculated, student, you already calculated that tau d tau 1 value and d tau 2 value I already told you. Again I am telling you that d tau 1 and d tau 2 value what? D cube, no? Something d tau 1 is equal to d cube p1 by 2z cube, and d tau 2 value d cube p2 by 2z cube. Okay. In our last equation, I think we wrote dp cube. Okay, so please change and correct the term as d cube p. Okay, now it is not dp cube, it is d cube p by 2z cube. So these are your d tau 1 and d tau 2 value, and your this value, this whole value is I am writing here. So how we can calculate this? We just it is e square by r1 not, no? So what they are doing here, first I am writing e square by r12 is equal to integration of, we write that values, psi values. Okay, psi values we write. What are psi values? Psi values I already told you here. These are psi values. Okay, psi 1, psi r1 value is this, and this is psi 2 value. Okay, so we are writing here psi values r for r1 and r2. So z cube by pi a naught cube we put outside, z cube by pi a naught cube. Okay, then integration of, okay, then integration of that because double integration of e power minus 2z by a naught into r1 plus r2 into e square by, this is as it is, sorry not d, it is e square by r12 d tau 1 d tau 2 is here, no? So I will write these term at the place of d tau 1 d tau 2. Okay. Now this is not 2 minus 2z r1 by a naught minus 2z r2 by a naught. So 2z 2z r1 by a naught is equal to p1 and 2z r2 by a naught is equal to p2. Okay, students. So now r1 is equal to what? R1 is equal to p1 a naught by 2z. From here r1 is equal to this down and a naught is in uh, multiply by p1. Okay. Now r2 is equal to p2 a naught divided by 2z. Okay, students. Now r12 r now r12 is what? R12 is p12 a naught by 2z. Okay, now r1 is equal to p1 a naught by 2z. R2 is equal to p2 a naught by 2z. So r12 is equal to p12 a naught by 2z. Now dr1 is equal to dp1 a naught by 2z and dr2 is equal to dp2 a naught by 2. All things we have, all things we got. Okay, all these terms put in this equation and finally what we will get? E square by r12 is equal to, it is common, z cube by pi a naught cube, double integration of, now what we have, e power minus 2z by a naught, r1 plus r2, no? So at the place of r1 we will put this, r2 we will put this. Okay, so this is multiply inside. Okay, na? So this is equal to p1. So e power minus common p1 plus p2. Okay, 2z r1 by a naught is what? 2z r1 by a naught is p1. So we will put p1 plus 2z r2 by a naught is equal to p2. So we will put p2. Okay, students. Now into e square by uh, e square by r1. So first they are putting r12 value. R12 value. E square we are putting here. E square. Okay. Now 1 by R12. So R12 value is this, but it is 1 by, so 2z upper. So 2z upper, so 2z by P12 A naught. Okay, students. Now d tau 1 and d tau 2 is there. So d tau 1, what? Where d tau 1? D tau 1. Yes, here. D cube P1 by 2z cube d cube P2 by 2z. Okay, students. Now, when we solve all these terms, means 2z cube, 2z cube, so 2z power 6. Okay, we put outside, so z power 3, z power 6 cancel out, so something. Okay, so I am writing here final e square by r1 2 average is equal to 5 by 8 5 by 8 z square by a naught. Okay, student. Now, in that equation, that Hamiltonian, put this value. That Hamiltonian, first value is what? In your, yes, this z square by a naught minus 4z square by a naught plus at the place of e square by r12, we will put this value 5 by 8. Okay. So, z square e square. This is, yes, sorry, z square e square by a naught minus 4 z square by a naught plus 5 by 8 z square by a naught. Okay. Now e square by a naught we can put common inside, z square minus uh, e square by this common, no? So z square is there minus 4z from here plus 5 by 8z here. So 4z plus 5 by z what? 27. It is e square by a naught into z square minus 27 by 8z. This is your final Hamiltonian, student. Okay. So as we know, the value of z, okay na, the value of z is proton value na, charge of proton. So we know that the value, we know the charge of electron. So all these value we know. So we get H Hamiltonian is equal to how much? Minus 77.5 electron volt. Minus 77 by 77.5 electron. Okay. When we put all these value e square, then a naught value is something. Okay. All constant values. So this value we know that is very small value, minus 77. Okay. So that Hamiltonian is for ground state Hamiltonian, and it is always less than from the first excited state. Okay. The first excited state of helium, how much? How much the first excited? This is the ground state of helium. 77.5 electron volt is ground state. Okay. It is ground state of helium. Then uh, by perturbation method, we calculate here. Okay, no, we calculate it. So it is always less than for the first excited state value and other excited state value. This is your proof of variational method. Okay, students, understood? All of you?
Yes, ma'am.
Yes, ma'am.
Okay. So, in our next class, we will study about that Landes interval rule. Actually, this Landes interval rule is same as in your atomic and molecular physics. Just you wrote the exam, no? So it is
Yes,
very much
ma'am.
similar. So you just see once this Landes interval rule, and if there any problem, so ask me. Okay. So we will go directly on the uh, perturbation theory for degenerate system. Okay, na?
Okay,
Or
ma'am.
degenerate perturbation theory. Our next topic is degenerate perturbation theory. So before this, you just see once that Landes interval rule. Okay?
Okay, ma'am.
Okay, students.